That's the one that I'm referencing. Is everyone on the classroom? The Google Classroom? Not yet. Okay, do I have to invite you? Oh, okay, I'll do that. Okay, so I will, yeah. So at the end of the class, when I flip my computer back over, I'll type the code into the chat. And then there's also nothing on it right now, so it's not like you're missing anything. And that's where I'll put this note. I'll put the periodic table I'm referencing and a little, practice sheet if you want to try it with the answer key. Okay, so based on this information about sodium, oh, no problem. Thank you for letting me know. I just assumed that everyone was on it. How many protons would there be in sodium? Sodium is a very reactive metal. Yes, 11. So the protons is the same number as the atomic number. I do like to color code everything so that if you look back at it later. Oh, now my color coding is a little bit. Okay, well, just start talking about color coding and now it's not letting me change the color. That's cool. How about the neutrons? Okay, I'm gonna hit refresh. And go back in. Sometimes that works. Just doesn't want to. Oh, I don't want to be stuck in red. 1 second. Okay, so while I try and change the color here, think about the number of protons, neutrons, and electrons. I really enjoy the colors. That's why I want it back. Let's try this. There we go. Okay. Yeah, so we have to round. Oops. So we have to round the atomic mass to the mass number. So 22.99, anything 5 and over rounds the number to the next. So the atomic or the mass number will be 23. And neutrons are always the mass number minus the proton number. And like Caden said, that will be 12. And then how about the electrons? Yep, the electrons will be the same as the protons for now, which is the same as the atomic number. So I can go ahead and put that into the nucleus of the atom. And then around it, I will put the electrons. Now I just have to be sure not to put the electrons on the nucleus. It has to be on the next circle or the next orbit. We can also call it a shell. Those are all words you might see for it. All right, so how many electrons in the first shell or orbit? 2, yeah. Oh yeah, something happened in the chat here. So yeah, Michael said if it's neutral, yeah. So we haven't gotten to ions just yet. Okay, and then I still have to go up to 11. So in the next one, I'll put 1. So I'm at 3, 4, 5, 6, 7, 8, 9, 10. 8 is the max for that one. So I'll put my 11th there. So then how many valence electrons here? Yes, only one. So this one electron is the electron in the outer shell, the last shell. So there's one valence electron. How many shells or orbits for sodium? Like how many total circles had electrons on them? 3. So 1, 2, and 3. So I asked this question because we could keep drawing these forever and some of them will get really big, but we can also go back to the way that the periodic table is arranged. So on the periodic table, actually, the column number can tell us, or the group number can tell us the number of valence electrons. But we just have to be careful that we're skipping the transition elements. So we don't consider the transition elements in this pattern. So what I mean by that is when I'm looking at this, I'm going to say, okay, hydrogen will end up with 1 valence electron, 1 electron in its outer shell. Beryllium will end up with 2. When I skip the transition metals, I'm also skipping their counting of the family or the group number. So boron ends up with 3 valence electrons. Carbon and the rest of the column end up with 4, nitrogen 5, oxygen 6, fluorine 7, and neon 8. Helium's a bit of an exception. Helium will have 2 valence electrons, not 8. Okay, so the second number of the 10s there is what coincides to the number of valence electrons. The row number or the period number also gives us information about the Bohr-Rutherford diagram. It tells us the number of shells or orbits that the diagram will have. And to read the period number, we just don't want to forget about period 1, where we have helium and hydrogen. And then we just number down. Okay. So if I said which element is in group 15 and period 2, which element would you say that is? Group 15 and period 2. Yeah, nitrogen. So as an example, nitrogen here is in group 15 and period 2. So it's almost like a coordinate for an element. Okay. And if I were to just show you how that trend works, well, look here. So oxygen, we said, has 6 valence electrons, and we've drawn 2 shells. If I look back up here and I find oxygen, I see, oh, yep, 6 valence electrons. I see that from the red number. So 6 valence electrons from its column number. And yep, I needed to draw the 2 shells that the period number tells me to. So the drawing will coincide, at least for the first 20 elements. After that, things start getting really weird. But for the first 20 elements, it will coincide to the diagram. Any questions about that? Yes, so if we look at a full periodic table, my sodium would be right here. And so sodium is in period 3. So yeah, we had 3 shells and it is in group 1. Yep, so one valence electron. Should we try another one? Or should we move on to the next, kind of elaborate this idea a little bit? How do we feel? I'm going to take the silence as ready to move on. So that's how atoms, the atomic form of an element will exist in reality, or in a simplified reality as our Bohr-Rutherford diagram. And as someone had suggested, like when we were talking about elements, they said, oh, H2O. H2O is a compound. It's made up of many elements. Before some elements enter into a compound, they're going to form what's called ions. And ions are charged atoms. And they're charged because we change the number of electrons. And the reason we change the number of electrons is because before elements enter into a compound, so before they start combining, or not before, elements will combine with other elements to form what's called a stable octet. So like we see here with nitrogen, nitrogen only has 1 electron in its outer shell. Oxygen has 6 electrons in its outer shell. Atoms will join with other atoms to create what's called a stable octet. And a stable octet means max number of electrons in outer shell. So I'm going to start using that short form for electrons, the E minus, just for simplicity. So sodium, for example, naturally exists like this with 1 electron in its outer shell. What's encouraging it to go into a compound is to obtain a stable octet, so to have 8 electrons in its outer shell. Same thing with oxygen. It only has 6 in the outer shell. It's encouraged to go into a compound to have 8 in its outer shell. And there is a way that we can predict how that's going to happen. So if I look at oxygen, again, I'm going to draw the Bohr-Rutherford.